All right, so the first thing that we will cover are real numbers, and then we'll do a section on fractions and decimals. So we will do the first half of real numbers in this little mini video. Okay, before we do anything, I just want to go over some definitions, just so that we kind of are all on the same page. Set notation. Set notation uses curly brackets. So curly brackets contain the elements or the members of the set. The set might be the members of our class, it might be numbers, it might be colors, but whenever you see curly brackets, you know it's a set. That little funny E symbol just means a member of or an element of. So that would say Beth is a member of our class. We wouldn't really use element of for a person. Natural numbers are the first set that we'll talk about. So we've got our curly brackets, and those are just the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. The notation for natural numbers is that funny looking N. Integers. Those are all the natural numbers, but then we include the negatives of the natural numbers in 0. So those are kind of like our whole numbers. Whole numbers technically mean something different, but it's what we think of being a whole number. And the notation for that is that fancy Z. Are these the only numbers? Now, several hundred years ago, mathematicians kind of thought they were, and then they realized that they were missing some. With fractions and decimals, they knew that we had those. So rational numbers there's the set of P over Q. That vertical line means such that P and Q are elements of the integers, so that means P and Q are whole numbers, and Q can't be 0 because we can't divide by 0. The notation for that is this fancy Q. And one thing to note, a rational number is any number that can be written as a fraction. It doesn't necessarily have to be written as a fraction at that time. So if you have 0.7, that's 7/10, so that's a rational number. In other words, if the decimal form either terminates, that means it stops, or repeats, you know you have a rational number because it can be written as a fraction. Okay, so if we look at how these numbers all fit together, we have our natural numbers, that's the smallest set. We make the set a little bit bigger and we get our integers. We make the set a little bit bigger and we get our rational numbers. Because all of our integers, all those whole numbers, they can be written as a fraction. Like 3 is 3 over 1. It can be written as a fraction, so it belongs inside of the rational numbers. Now, are these all the numbers? Now, back to what I was saying before, this is what mathematicians used to think was everything. And then they realized that there were some numbers that aren't being included, and those were the irrational numbers. The first one they discovered was the square root of 2, and that led to all the other square roots. And then pi and e and other numbers like that, where the decimal form doesn't stop and it doesn't repeat. So just again, rational numbers can be written as a fraction. That means the decimal form either terminates or repeats. Irrational numbers can't be written as a fraction. That means the decimal form doesn't stop and it doesn't repeat. So if you did square root of 2 on your calculator, it would just keep going and going without repeating. Putting that all together, we get the real number system, which has this fancy R as its shorthand. Now let's look at a few numbers and where they fit in here. If we have negative 3/5, well, that's a rational number, so it belongs in this green circle. But it's not a whole number, so it can't move into the blue circle. So it has to stay right there. Square root of 6. That can't be written as a fraction. If you did it on your calculator, you'd see that this decimal form doesn't stop or repeat, so it belongs outside the green circle. 0.22222 repeating. Since it's repeating, it can be written as a fraction. Don't worry about what the fraction is. I'll show you if you're interested. It's actually kind of fun, but we just don't have time to cover it in this class. So it can be written as a fraction, so it goes in the green circle, but it's not an integer, so it can't move any further in. Negative 51. That can be written as a fraction, like negative 51 over 1, but it's also a whole number, so it gets to move in even further. 15 over 3. Well, that looks like a fraction to me, but 15 over 3 is really 5, so it's a whole number, but it's actually a positive whole number, so it moves all the way in to the red circle. 5 is a natural number, and 15 over 3 is the same thing as 5. How about 0 over 2? Well, it's a fraction, but 0 over 2 is really 0. So it gets to move into the blue circle. It's one of the integers, but it's not a positive integer, so it can't move into the n. So that's just kind of the numbers that we'll be working with in this class. We won't deal with any numbers except real numbers for this class. So those are our definitions. Next slide, this is the shortest one of all, is ordering of numbers. And we're just going to take all the numbers that we had that we put into the circles and put them on a number line. So -3/5, I don't care about it being perfectly exact, but it's between 0 and -1, so we'll put it right there. Square root of 6, I'll show you how to do it without a calculator next time, but for now, is between 2 and 3. You'd know that if you just used a calculator. It would be 2 point blah, blah, blah. 0.2222222. Well, since it's 0.2, it's between 0 and 1, so it belongs about there. Probably should shift that dot a little to the left, but it's close enough. -51 is clear down there. We don't have room for it. 0/2, well, it's the same thing as 0, so it belongs right there. And what about that 15/3? Well, 15/3 was 5, so that one belongs there. I know that's pretty easy, but we'll need a concept of a number line in order for our next definition to make sense. Okay, our next thing is inequalities, and this is something everybody's probably seen before, A less than B. Now, it might not make total sense what that really means, because if somebody said, what does it mean? You say, well, it means B is greater than A, and that's just kind of circular. What it really means is that A is to the left of B on the number line. One number is less than another if it's to the left of that number on the number line. So what do these guys mean? Well, they're greater than, less than or equal to, greater than or equal to, not equal to, and the only one you probably haven't maybe seen is the squiggly equal, which means approximately equal to. Okay, an example of using our inequalities. This example is very, very easy, but there might be one or two places that get a little bit tricky, so let's just look at this. If I want to compare these elevations, now rather than just going through and filling on the less than or greater than signs, I'm going to put the numbers in there so that when we go back and look at it, it will make a little more sense. So Houston 0, the elevation of Cincinnati is 433 feet above sea level. Well, obviously 0 is less than 433. Super easy, I know. Then we have New Orleans and Chicago. Well, -8 is to the left of 579 on a number line, so that one's less than also. Super easy still. -8 and 0. Now 8's bigger than 0, but -8 is less than 0 because -8 is to the left of 0 on a number line, so we'd still have less than. Cincinnati and Turpinpendy. I had to kind of get random cities to get elevations that did what I want them to do. Now if we have a positive number and a negative number, obviously the positive number is bigger than the negative number. That one's not too hard, even though 505 is bigger than 433. Well, how about Turpinpendy and New Orleans? 500 is bigger than 8, but -505 is to the left of -8 on the number line. So we have a less than. And if we have these two, -154 is to the right of -505. So -154 would be greater than the elevation of Turpinpendy. If you were to make a mistake, I know they're pretty straightforward, but if you were to make a mistake, where would it be? It's possible you might get a little thrown off by that, but I think you'd be fine. The one that I would see people getting thrown off on are these last two, because 500 is bigger than 154, so sometimes when the negatives are thrown on there, it turns people around a little bit. So just look at that for a minute and make sure that it makes sense. Okay, just as a kind of validation that people actually do have a hard time with this sometimes, is an article that was in the Manchester Evening News about a lottery game. And to win this lottery game, they had to scratch off a temperature that was lower than the other temperature shown. And when they scratched off a number like -7, they thought it was actually lower than -8. And anyway, that article is there if you'd like to pause and read it, but I'm not going to take a lot of time to go through it. It's just kind of an interesting example that a lot of people really do have problems, so much so that they had to withdraw an entire lottery game from England. Okay, those are our inequalities. So let's go over opposites and absolute value quickly. Two numbers are opposites if they're the same distance from 0. The opposite of the number a is negative a. Now sometimes I'm going to say negative a and sometimes I'll say the opposite of a. Most people are used to saying negative a and that's totally fine, but I want it to be okay with you if I say the opposite of a. The absolute value of a number is the distance from that number to 0 on the number line. And since distance is not negative, the absolute value is never negative. So if you have the absolute value of a positive number, it stays positive. The absolute value of a negative number becomes positive. An absolute value is denoted by two vertical bars that we'll see on the next slide. So we'll just see those in the later examples. First of all, with our inequalities. Negative 27 and 10. Well, negative 27 is less than 10 because it's to the left of 10 on the number line. 5 halves is less than 5, not too hard. Now this one throws people off. People want to cancel those negatives and you can't. Those vertical bars mean absolute value, so ignore the first negative. Absolute value of negative 2.9 is just 2.9. And then you take the opposite of that, so you have negative 2.9 is less than 2.9. Okay, let's look at this next one. Now it's kind of long. We just have one inequality to fill in, but let's simplify first. The absolute value of 4 is just 4. Okay, so far so good. Absolute value of negative 6 is 6. Good. Okay, now before we can figure out the absolute value of the numbers in the next one, we have to simplify the inside. 2 minus 10 is negative 8, plus 16 is positive 8. So we're going to take the absolute value of positive 8. And then the absolute value of negative 5 is 5. Notice again, those negatives don't cancel. We find the absolute value of negative 5, which is 5, and then we subtract that. Okay, so this next step, the only thing we need to do is find, first of all, what 1 minus 4 is. 1 minus 4 is negative 3. Absolute value of 8 is just 8. Okay, just doing one thing at a time. So we have negative 3 on the left. 6 plus 8 is 14. Minus 5 is 9. Minus 11 is negative 2. So negative 3 and negative 2, which one is bigger? Okay, negative 3 is to the left of negative 2 on the number line, so negative 3 is less than negative 2. That finishes opposites and absolute values, and we will go on to the next video for the next stuff.